So, good morning, everybody. I will actually deliver the message from the government, which is actually from the Ministry of Environment at the end of my presentation, since it has a lot to do with my presentation about the CarbFix project. So, just a general outline on CCS. The climate goals will not be met without widespread application of carbon capture and storage. And this is not only for the fossil fuel burning power plants that we foresee that will remain part of the energy grid for at least some decades in the future, but also to deal with emissions from industrial processes such as cement production, steel production, aluminium production, and other processes that we will still need to rely on, even though we would be able to somehow phase out fossil fuels. And then, as the IPCC report from 2018 states, we will need to rely on some negative emission solutions during the latter half of this century, and CCS will be one of the technologies that could provide this negative emission pathway. These are the cumulative emission reductions that are needed to achieve the goals of the Paris Agreement, according to the International Energy Agency. And as you can see, CCS is supposed to play a really significant role in the emission reductions. And about 119 gigatons or billion tons of CO2 are expected to be stored via CCS before 2060. And just to put this into perspective, we are currently injecting about 40 million tons annually, and this is mostly in connection with enhanced oil recovery. So at this pace, it will take us about 500 years to sequester these 190 gigatons needed. So the pace of CCS has been way too slow. We have to really accelerate this if we are somehow going to be able to store all of this CO2 before 2060. So most of the ongoing projects are injecting CO2 in liquid or gaseous or supercritical phase into sedimentary basins, where we have this cap rock that prevents the CO2 from leaking back to the surface. But in Iceland, we have been developing an alternative solution where we dissolve the CO2 in water prior to or during injection into reactive basaltic rocks. And by dissolving the CO2, we are actually killing the buoyancy. So this CO2 charged fluid doesn't have the tendency to rise back up, but rather to sink, since it's actually heavier than the groundwater that is present in the formation. So these are the ingredients that we need. We need basalts or other reactive rocks, and basalts are very optimal for this process, since they contain about 25% of the cations that we need to, in order to mineralize the injected CO2. So this is basically the chemistry behind it. So this method, it's not going to replace the conventional CCS, but rather this is something that could be applied in areas that have not been considered suitable for CCS up until now. So this might be a tool to add to the toolbox, to the potpourri of solutions that we will need to look into in order to achieve these goals that we have set in this huge task that is ahead of us. Basalts are actually the most abundant rock type on surface on Earth. It covers most of the oceanic floor and about 5% of the continents. Iceland is the largest landmass above sea level, and it is about 90% basalts. So it's actually the perfect spot to develop this method further. And that is what we have been doing since 2007 when this project was founded. For the first couple of years, it was mainly evolving around lab experiments and storage capacity estimates. But we started our pilot injections in 2012, where we injected about 200 tons of CO2 into the basaltic subsurface near the Hellisheiði geothermal plant in Iceland. The results were very promising for this method. We could prove that over 95% of the CO2 that we had injected had mineralized within 2 years of injection. So this was much faster than previously thought possible and changed the timescale of CCS quite significantly. So this is actually a figure that demonstrates these processes when you inject into sedimentary basins. It's a figure from Sally Benson from a CCS IPCC report from 2005, and it shows these trapping mechanisms that the conventional CCS relies on, where you inject into these sedimentary basins and have this impermeable caprock to prevent the CO2 from rising to the surface, and then eventually the CO2 gets dissolved in the fluid. And then if you have some cations in the aquifer, finally you will mineralize some part of the injected CO2. But we are actually achieving solubility trapping by dissolving the CO2 during injection or prior to injection. So it happens within minutes. And then we rely on the mineralization, which occurs within a few years. So this is the process as it is for now. So in 2014, this process became just an integral part of our operations at the Hellisheiði geothermal plant. So we have been injecting annually about 12,000 tons per year at the rate we are now. So this is the process we produce out of the production wells, and this is a two-phase fluid. We flush at the wellhead and the steam goes into the turbines, and we use the brine to heat up cold groundwater for the district heating system in Iceland. But then we capture the gases and we take them to our gas abatement plant, which is just a shower where the gases get dissolved in a condensate from the turbines. And then we inject this CO2 charged fluid into our injection system. We have quite an extensive injection system at the site. We have about 18 re-injection wells, and we are annually injecting about 25 million tons of fluid back into the aquifer after the production. So this was quite a simple procedure to apply. We retrofitted 2 of these wells to be able to receive the gas, and this has been running smoothly since then. So this is how we've been stepwise scaling up our operations, and as you can see, we are injecting now about 1/3 of our CO2, and the aim is to go zero emission, and we are now actually in the phase of planning the next steps and doing a design on our next capture plant. So in order to make this go up, we will have to add a new scrubber to our system, and that's the aim in the near future. The cost of our operations in Hellisheiði is about $25 per ton, and this is actually comparable with the current price of the carbon quota at the European carbon trading scheme. So since the price of carbon has been rising somewhat, it's of course always going up and down, but since probably late last year, it actually, we managed to meet the prices of carbon, and since then we have really felt increased interest in applying this elsewhere. So the future of CarbFix, we are now trying to explore all possible ways of making this method as applicable as possible in different environments. We have since 2017 been running a pilot with a Swiss company called Climeworks, where we are actually capturing CO2 directly from the atmosphere and injecting it along with our geothermal CO2. And we are looking at a possible scale-up at our site. So we are now at the order of 50 tons per year, but they are looking into injecting at least 1,000 tons in the near future. Since our process is quite water intensive, we have also been looking into using seawater for dissolving the CO2. So we are now in the labs doing seawater experiments, and so far it looks very promising. In 2018, we started a project called Gecko, where we are looking into other types of rocks. We know that basalts are perfect for this process, but we need to set the boundary. We might have some rock formations that are not as good, but still good enough. So we are aiming on some pilot injections in Italy, in Turkey, and Germany. And then we are also extending our operations to our second geothermal plant in Iceland that is operated by Reykjavík Energy. And we will start pilot injections in 2021 at that site. This summer, a letter of intent was signed between Reykjavík Energy, the Icelandic government, and the heavy industry in Iceland. And since Iceland relies on geothermal and hydro for the energy production, there is actually a lot of stake if we manage to capture the CO2 from these processes, since they account for about 40% of current emissions in Iceland. So now we will look into ways to see if CarbFix can be a viable solution for these industries. So I just always like to end with this picture of Siggi Gíslason, the head of the scientific committee of CarbFix, blessing our injection well. So this is more or less where we are at as for now. And I hope that this method can be applied elsewhere and can provide at least some of what we need to achieve to make it and to achieve the goals of the Paris Agreement. And I will end with this message from the Ministry of Environment and Natural Resources. And the reason why this is brought to you is that one of the external advisors for this project is actually working at this ministry, and she was planning to come here, but asked me to bring this message for you, and I will just read it to you. The Ministry for the Environment and Natural Resources has been following the CarbFix project from the beginning with great interest. The Ministry is looking forward to results of the cooperation based on the declaration signed in June by the government, Reykjavík Energy, and the aluminium industry in Iceland. With positive results of this cooperation, the CarbFix method can play a significant role fighting climate change and reduce emissions in Iceland. The Ministry is looking into the legal formalities regarding the verification of the CarbFix method to be used within the ETS system. As the method is not defined as a conventional CCS, there are some issues that need to be clarified. Due to geological circumstances in Iceland, conventional CCS is not allowed. The Ministry looks forward to next steps in the process and further development of the CarbFix project, with the hope that it will not only be used in Iceland but also globally, wherever the geological circumstances makes it possible to be used to help fight climate change. So, thank you. Questions?
Sorry, I've got a quick question. It's very seismically active, obviously, in Iceland. Mm-hmm. Do you know how much induced seismicity you have, and how easy is it to separate from the natural background levels of seismicity in Iceland?
We have actually had severe problems with induced seismicity in the field where we are injecting now. So not in connection with the gas injection, but in connection with the re-injection of the fluids. We have established a traffic light system on how to go about injection since we ran into this event, which was, Reykjavík Energy was not very popular at that time. But it seems like the major trigger is to start too abruptly. So if you start slowly and increase gradually, we have managed to control this. So this has not been a problem since 2011, where when this site was commenced with quite some shaky results.
Thank you.
Hi, Sandra, and thank you for your talk. I have two questions. One of them is like in your map of where you're trying to expand the technology towards. There is like a little spot in the UK, and I was wondering what that could be. And my second question at the same time is, what kind of formation do you think you can expand this technology towards? Like, are you thinking only basalt, or do you think like maybe something like shale that still has some ions could work? Perhaps, I don't know.
Yeah, unfortunately, the red spots are only partners. I wish we would be injecting in all of these places, but I should have explained this better. The black stars are the points where we will be doing injections, and we are not looking at basalts in the Gecko project. Of course, we are going to be doing this in Nesjavellir, so we will be injecting into basalts there, but we kind of know what we are dealing with there. But we are looking at other types of rocks, so some volcanoclastic rocks in Turkey, there are some iron-rich gneisses in Italy. I'm not sure if this will work at all, but and then there are some sandstones in Germany that are like poorly. They have some stuff in them. They're not very clean sandstone, so we will see. But we will just have to try to figure out what, if something else is good enough for us. So.
Thank you, Sandra. A question, what is the ratio of the water to CO2? Because the solubility probably is not very high.
Yeah, we need quite significant amount of water. So we at our operations, we have the ratio of 25 tons water per ton of CO2. So there is a lot of water that needs to be used for this.
So thinking about this is, if you just inject the CO2, wouldn't that be maybe easier even for the reactions with the CO2 and the rocks?
So first of all, the formations are very fractured. So you would never want to inject gas into these basaltic volcanic areas. The permeability is fracture dominated. There are lots of earthquakes in the area, so we are constantly opening up new pathways. So we would never want to inject it as a gas. Also, by dissolving it, we are speeding up the process of dissolving the rocks and speeding up the process of the reactions. So it's vital to use the water, but if we can figure out a way of like injecting less water or injecting maybe in some parts like more gas at the beginning, more water, further on, something like that. This is just something that has to be optimized.
If you're creating new minerals, essentially, in the rock, is there any danger that you will damage the permeability around your injection well and reduce the injectivity? So
this is one of the beauties of this method, because the fluid that we inject is acidic, so these minerals are actually undersaturated in the vicinity of the injection well. So we are rather dissolving close to the well, and then as the fluid reacts with the rocks and flows away from the injection well, we start to account the the conditions for the carbonation. So this is not occurring in the vicinity of the well itself. So the permeability of our injection well has improved or stayed the same. It has definitely not gotten worse since we started injecting, and that was in 2014. So.
Thank you.
Sandra, the discrepancy between, you've shown that the discrepancy between the requirements, the rate at which we're doing it, at what is necessary is really large. Mm-hmm. So beyond the type of rocks, what are the key points which are missing to scale up?
So I don't think, the technology is in place and the knowledge is in place, but it's not science that is holding it back, but rather probably just the cost of it and the lack of incentives for the industries to go this way. As for now, it has been much cheaper to just emit the CO2. So maybe when the prices start rising, and that's actually what we are experiencing now, that the interest is, we are definitely getting more interest in actually applying this method elsewhere. In the beginning, the industries were just interested because they thought it was a cute experiment, but as for now, when the prices are going up, then maybe there is something that pushes them forward. So I think political and financial things rather than scientific barriers. And then of course we need to do some more upscaled projects to gain the experience that we need to, we want to scale up gradually and learn from the experience. So that's probably mostly what's holding it back.
Many thanks for your presentation. You show that the monitoring cost quite high, $9 per ton of CO2, almost 50% with respect to capture. What
0.5, I think.
I know,
0.9.
0.9.
Yeah.
Sorry.
Yeah.
In any case, what's the techniques that you are using?
So we are mostly relying on traces. So we do regular tracer tests to just make sure that the pathways are remaining the same, and also so we are able to do mass balance to calculate the rate of mineralization. We do some CO2 surface monitoring as well. So that's mostly what we've been doing. Yes, we have some extra seismic stations around our injection.
Thank you.
Thank you. You said you said a couple of words about expanding to different types of rocks. I'd be interested if you could just say any more about that in terms of the type of minerals that need to be in the rocks, whatever type of rock it is. And then secondly, you presented some very exciting, timescales for the mineralization with this project. And I'm wondering to what extent the temperature is important on that. Do you also need to look at areas where you have relatively high temperatures near surface to get anything like those timescales? So
I'll start with the timescales. So this figure is from our pilot injection that was actually at 20 degrees. So it was not the high temperature operations that we are running now, which actually show that we are speeding this up further. So we are actually seeing it happening even more rapidly, but these are just such extreme conditions that, it's not to be replicated in many places. But so this is, close to just ambient temperatures. In terms of different rock types, so we need these cations. We need calcium, magnesium, irons to mineralize. We mostly see that calcite is precipitating. So, but this is of course very dependent of the conditions. So, yeah, what we will be looking into at the Gecko project are the possibly suitable formations at these sites. So these volcanoclastic rocks in Turkey, and some gneisses that we'll see if work at all, and these unsorted sandstones in Germany. But we don't know much about this in other, basalts and or just mafic and ultramafic rocks in general have been the rocks that we have been focusing on mainly. There is some work ongoing now in terms of mine tailings and in looking into the different composition of the rocks and grading them in green for really good rocks, and then we have these ones that are in between but might be good enough. So this is just something that has to get some more focus, and we'll see if we can apply this elsewhere.
Thank you.
Do you also here? Do you follow the status of the biodiversity, bacterial biodiversity that is living underneath, and how do you manage this?
So this was done during our pilot injection in cooperation with Benedicte Mendes Group in France. But the reservoir that we are injecting into now, it's sterile. It's way too hot for any microbiological activity, so they were not interested in following anything there. So, but we did see some microbiological blooming during our CO2 injections into the colder reservoir. But the source of carbon in bacteria was like orders of magnitude lower than the inorganic carbon. So it was not interfering with our operations in that way, but it's definitely something that has to be looked into.
Okay, so I think if we have a further question, we can take it during the panel discussion, and we can go for the next.
Good morning. My name's Douglas Connelly. I work at the National Oceanography Centre in Southampton, and I'd like to present some of the work we've been doing as part of the STEMM-CCS project, which is funded by the European Commission. We started in 2016 and we finish next February. We have 13 partners across Europe, including one industrial partner, which is Shell. Shell have been very supportive of this project from the very start. The onset, we were originally tied to a demonstration mission that Shell had proposed, which then, due to a change in government policy in the UK, they cancelled that at the last minute. But we still, Shell are fully committed to the project and have been very supportive. Partners are all over Europe. They represent some of the most advanced research in offshore carbon capture and storage. Our project is entirely around offshore carbon capture and storage, and we're really concentrating on this sort of leakage impact and assurance monitoring. We're not involved in the capture, we're just involved in what you do with it once you've got it. And obviously for the European milieu, the offshore CCS has been proposed as one of the most propitious ways of storing carbon dioxide, in as much as we have lots of depleted oil and gas reservoirs offshore, and also with the existence of the now Equinor operation at Sleipner, we have the longest running offshore carbon capture and storage facility in Europe, actually in the world. So we are interested in actually, if you put CO2 under the seabed, what happens if it starts to leak? Now, at the moment, the main monitoring that's been occurring at the Sleipner field has been around 4D seismic, so plotting the movement of the plume of saturated CO2 into what has been into an aquifer. So the difficulties arise is if it actually breaks out of the cap rocks, the covering area around that, what happens, how do you find leakage? And also you've got a large scale issue. So the Shell platform that we're going to use for storage for carbon capture for carbon dioxide is called GoldenEye. The aerial footprint on the seabed is 140 square kilometers of seabed. For the Sleipner, they're using the Utsira formation. It's about 1,600 square kilometers of seabed that you have to monitor. So if you go beyond having to look at things from seismics, how do you actually look for leakage? So one of the things we're looking at is we're not interested in this deep reservoir release because the seismics would pick up on that. We're really interested in this overburden bit. So actually where the CO2 starts to impact basically the environment that we see, so the marine system and the sediments. One way of looking for it, of course, is to actually look at dissolved CO2. So can you see or bubbles of CO2? If you've got a large leak, chances are there'll be bubbles. Bubbles are relatively easy to find in marine systems. They're acoustically active. You can measure them from acoustics from ships. Your classic fish finder works by measuring bubbles. You can also look at the release of fluids that are pushed out. Since CO2 as it rises will produce an acidic fluid, it will dissolve things like iron, manganese and hydrogen sulfide and push these compounds out into the marine environment. So therefore you could look at those to find ways of finding the release. To do this, since we're somewhat lacking in natural release source of CO2 in the North Sea, we decided we would do a release experiment. I did this basically sitting on a ship in the Pacific, wrote this little schematic and thought this would be easy. I'll just lower some CO2 bottles to the seabed. We'll drill a pipe a couple of meters below the seabed. We're only interested in that overburden bit, the sort of upper 5 meters of the sediment. We'd release CO2 and then we'd throw basically all the tools we have. So ships, autonomous vehicles, landers and sensors in the water column to see what would happen when the CO2 is released. This proved not to be quite as simple as I thought it would be. As soon as we went to try and buy cylinders of CO2 and we said we're going to put them on the bottom of the seabed, the supply companies ran away and said we won't do that because there's a risk of it exploding or whatever and it would create problems. So the other thing that was an issue was drilling this pipe. We wanted to do this basically we wanted to put the CO2 reservoir relatively far away, put an arced pipe. The reason it has to be curved is because if you release CO2 and it's a straight pipe, the chances are the CO2 will just go straight back along the pipe, the annulus that you've created from pushing the pipe through. So we went to a few companies, we put a tender out to how to do this. Lots of companies will draw you a pipe, as long as it's 2,000 or 3,000 meters one direction. They don't like doing this. And so we eventually got a company called Cellular Robotics, who now got a European operation as well as a Canadian operation. And it's not really a drill, it's actually this system here. And effectively it's a hydraulic winch. And it's about, well, I'll tell you here, it's 2.3 meter cubed, it weighs 6 tons. We lowered it to the seabed. The hydraulics of the ship actually just push the pipe through. And then we went down and we used an ROV to connect our gas supply to it. The glass supply itself was a bit of a challenge, in as much as I say, they wouldn't allow us just to use cylinders. So we had to have a bespoke system made. This was built over in Romania and shipped to us. And it contained 3 tons of CO2. It weighs nearly 13 tons in air, actually, not just 12, it's 13. It's probably one of the heaviest things we've delivered from one of our research vessels into the North Sea. We wanted to do this in real conditions. So this is actually done at 120 meters in the North Sea over the GoldenEye platform. So it's the world's first experiment where we've actually done a real life release in environments that would be where CO2 is going to be stored. To then look at what we developed to look at this. Now, one of the issues around the North Sea and around any environment is actually what your baseline is. So what does normal look like? So we put a lander system down in the North Sea. This is at 120 meters, right near the platform. It was there for 2 years, and it was collecting data the whole time. We wanted to actually get an idea of what was normal. So when you start perturbing the system by adding your CO2 from this artificial release we did or from a leak in the future, what does it look like? One of the problems, of course, is we are already adding CO2 into the marine system due to our impacts from anthropogenic emissions. So your baseline isn't level. Your baseline is constantly moving up slowly. So you need long time frames for looking at monitoring and the baseline. So we had a lot of new systems here. We've got these are so-called lab-on-chip systems. They're small little chemical labs that sit on a chip. They're about the size of this. They can be deployed for 2 or 3 years. They can measure nitrate, pH, phosphorus. We bought off-the-shelf materials as well, such as the CFOX system, which is a pH system that was developed a few years ago by Honeywell. And then we had regular current meters and some new optodes we've created. The project was a series of new developments, so new sense developments, as well as existing. The idea would be that you could work towards something an operator of an offshore carbon capture and storage facility could buy within the next few years. So the lab-on-chip systems are going onto market at the end of this year, and the other systems are already on the market. We used an off-the-shelf autonomous vehicle called the Garvia, which is developed by Teledyne, and we put sensors over there. The idea of using off-the-shelf systems is, again, off-market. Operators understand them because they use them all the time. They use remote-operated vehicles, and they're using more and more autonomy as time goes forward. The idea is to get away from using ships. If you have to monitor 140 square kilometres of seabed on a very regular basis, it's going to be prohibitively expensive using a ship at $25,000 a day. So the idea of using these autonomous vehicles is you could basically, they fly down to the seabed, they can mow the lawn, effectively go across the seabed, 10, 20 metres apart, 10 metres off the seabed, and just monitor large areas of the seabed over time. As you can see, this was actually the experiment we did. We had incredible weather. This is May and June this year. We were stunned at how good the weather was. And so we then put our system down. We put the gas cylinders on the seabed. I'll show you a little video in a minute. We started then to release the CO2. We were a little bit concerned about how the CO2 would react as soon as we put it into it. Would it just blast straight out? So we did a very slow release. I basically started off at 2 litres per minute, went up to 50 litres a minute. And we released it with this 50 litres a minute release is equivalent to a leak of 48 tonnes per year, which is at the lower end of what's acceptable under the legislation looking forward. So we wanted it to be realistic as to what you would actually try and find. And then we literally threw everything we had at it. So we used ROVs. This is a nice little system. This is basically using our remote-operated vehicle system, our little remote control submarine, with our pH optodes on there. You can see the release is here. Coming upstream into the release, you can see the CO2, the pH changes in the water column due to the CO2 release. We've stepped these off so you can see the different reactions. Coming upstream, you wouldn't see a release of CO2 if you approached the release from the upstream, but as soon as you went over it, you could see a perturbation there. One of the things we're also interested in is not just release detection, but it's actually how you could quantify it. So quantifying releases is quite difficult. You'll see some video in a little while of the bubbles. You can measure the bubbles. We've developed a lot of technologies around measuring bubbles, both from in situ and also from ships. But one of the things we wanted to look at was eddy covariance. Now, what eddy covariance does, you put a system on the seabed, and it effectively looks at a statistical cone, and it measures changes in pH. As long as you've got some fast sensor technologies, you need to be able to get fast response sensors that can measure both current speed, direction, and then your analyte of interest. So in this case, it was fast pH sensors. You can then back calculate your releases of CO2 by measuring changes in pH or total alkalinity or CO2. So we had a whole series of sensors addressing the same thing. One of the things we also wanted to do, particularly driven by our partners Shell, was to look at ways of avoiding false positives. Operators are extremely sensitive to accusations of basically, this is a leak and it's entirely due to your operation. And actually, it may be something natural. There's a Japanese operation called Tamakamai, and they fell foul of this a few years ago, where they'd done a year of measuring pH in the water column. They were injecting CO2 into their release, into their reservoir just offshore. All of a sudden, the pH dropped in the environment. The government stepped in and closed down the operation. And what it turned out to have been was a natural pH change due to a phytoplankton bloom, which had settled out and started to degrade on the seabed and lowered the pH just due to natural CO2 production. One method we're approaching it is to use a so-called stoichiometric approach, where we look at nutrients. So we measure nitrate, phosphate, and silicate alongside total alkalinity and pH. If your pH changes and your nutrients are also changing, that tells you you're getting a natural basically a breakdown product of a biological process. If your nutrients stay the same but your CO2 starts to increase or your pH drops, then you know you've got something out of the ordinary. So this is another way of constraining what is a natural compared to a leak from your reservoir. We combined all this with a lot of modelling approaches because obviously we're creating huge amounts of data. And so we've developed some methods to look at how you would model this system. So we're scaling down from sort of the regional down to the very, very hyperlocal scale on these, on the matter of meters on these models. So, and embedding them in our regular modelling approaches, such as a project called NEMO, where we look at the scale. We're also monitoring and modelling how the CO2 behaves once it's in the seawater. So you'll see here, you'll see the leak, hopefully if it works. So you can see the leak here. This is looking if our instruments are down here on the south. You can see the CO2 being swayed around by the tidal patterns. And again, you need a good control and a good understanding of what your hydrographic regime is. To put this into context with our data, we need to look at actually where we sat as far as releases. So these are the models around what would actually happen, environmental impacts. So this is where our release was. So we're about here. Small, low-level releases have been found to have no impact on the environment. The very large releases are usually very easy to detect because you generally get a blowout. There have been some blowouts, normally of natural gas, not CO2, obviously in the North Sea, for the simple reason we aren't doing CO2. But we're finding the biggest impacts actually in the North Sea are not due to hydrocarbon operations. They're generally due to trawling. I mean, you'll see some pictures from the bottom of the seabed in a minute. The environmental impact from trawling in the North Sea far outweighs, at the moment, any impact that Sleipner is having from CO2 storage and from a lot of other processes. Part of our project was to look at what naturally anthropogenic impacts there are already in the environment, again, around this false positives. If you start doing offshore CCS and then the environment starts to change and it looks like it's degrading, you need to show if that is actually due to CCS or it's due to other operations. Our monitoring strategy was, again, modelled as well, and what we wanted to do was determine, you could create, need to look at how far you'd have to do your surveys, how often you'd have to do your surveys, how far away you have to be from the release. So you can see here that the further away, the higher the release rate, the further away you can be from the release to actually find it, because of that perturbation of the CO2 and other chemical signals in the water column. And we're doing this to devise your optimal monitoring program. We're developing in the project a monitoring tool, which we're going to roll out for the offshore operators. And you'll be able to do a cost-benefit analysis of what particular processes are out there, what you could use, autonomy with a pH sensor, say, autonomy with just purely bubble detection. What would it cost, and what are your chances of actually detecting a leak, and what the scale of the leak would be. And so it's this idea of actually increasing confidence in our ability to monitor offshore carbon capture and storage. So the next steps we're doing is we're continuing the sense development. We're had another bit of a project we didn't really mention about here, which is the use of autonomy for image recognition. So on our survey systems here, we were photographing every 1 second the seabed, but of course that creates a massive number of images over an hour. And so we're looking at autonomous ways of actually processing all of that image processing, but I can answer questions on that separately. And we've also got a new project which we've just put in where we're going to shore launch this system here, which is a long-range autosub. We're going to launch it from Shetland. It's going to go out and it's going to monitor 2 oil platforms and a natural release point in the North Sea for methane, one of the POCMARK systems. And that's actually, it's related to CCS, but we're actually piggybacking it on decommissioning. So 2 of the platforms we're going to look at will be monitoring the chemical and biological regimes around the platforms over a month by just pushing this off the shore, monitoring it around, and these are the platforms that are going to be decommissioned in the near future. I'm going to show the video. This won't work here, but I'm going to go on to the next one. Before I get to that, if you bear with me 1 second, if I can get this video to work, because it didn't work earlier on. Right. This video is on our website. If you want to see, hopefully it will work.
Following 3 years of careful planning, preparation and technical development, an international team of scientists and engineers departed Southampton at the end of May aboard the RRS James Cook on a research expedition to the North Sea. Led by the National Oceanography Centre, the aim was to test sensors designed to detect escaping carbon dioxide in the unlikely event of a leak from a sub-seabed storage site. The site chosen for this experiment was close to Shell's GoldenEye platform, 100 kilometres off Scotland's east coast. Here, the team rendezvoused with project partners from the German research organisation GEOMAR aboard the research vessel Poseidon. The first stage was to use a specially commissioned drill rig built by Cellular Robotics, lowered 120 metres to the seabed to push a curved pipe into the sediment with its outlet 3 metres below the seabed surface. Next, the bespoke carbon dioxide and trace gas cylinders in their cradle were lowered over the side in a very delicate operation. They contained 3 tonnes of gas, which was to be pumped through the seabed pipe over 11 days to test whether an array of sensors could detect the deliberate release within the sediment, at the seabed surface, and in the water column above. The cylinders were connected via hoses to the inlet on the pipe using a work-class ISIS remotely operated vehicle, demonstrating the skill of the ROV pilots. Sensors were positioned around the area where the gas was expected to bubble through the seabed. These included optodes, acoustic detectors, and a range of other platforms carrying sensors to detect the chemical signature of the carbon dioxide and the tracers that gave it a distinct chemical fingerprint. The gas was turned on, and to a collective sense of relief and jubilation, the gas began to emerge through the sediment. Quite an achievement. More sensors were positioned to sample the gas, and even to film the bubble stream, with an optical array to capture how the gas behaves as it leaves the seabed. Gas samples were collected for later analysis, as it left the sediment, and within the water column. The local residents, an eel, an octopus and a Norway lobster, seemed more curious than concerned. Nearby, sediment cores were also taken for further investigation into how carbon dioxide reacts within the sand and mud. Back at the surface, a Gavia autonomous underwater vehicle armed with sensors was launched to take further readings in the vicinity of the release site. With the work completed and declared a great success, the ROV dived again to uncouple the gas supplies and retrieve the equipment from the seabed. The Strategies for Environmental Monitoring of Marine Carbon Capture and Storage, STEMM-CCS experiment, has shown for the first time in a real open water situation at depth that we now have the sensors that can detect even small releases of carbon dioxide. This should increase confidence that if a leak occurs, however unlikely, we now have the technology to find it and monitor its progress and effects.
So as you can see, it was quite a challenge all around, but it worked incredibly well. We were very lucky with the weather. As I say, we only lost 2 days in total to bad weather, which for the North Sea in May and June is incredible. It really was an incredible effort for everyone involved. I mean, most of the things we were doing in this project were new. All of the approaches were incredible challenges, both engineering and scientifically. We're just getting all the data together now. The early career researchers associated with the project are driving forward the paper development. In fact, I'm in Winchester tomorrow working with them for the first set of papers they're going to be publishing. Thank you very much. If you have any questions, I'm willing to answer any.
Is there any question?
Lady just there.
Okay.
Thank you. This was really, really interesting. It's amazing the different indicators, monitoring system you're implementing. And I was wondering, it's not real-time transmission, real-time data transmission. So how long would you collect the data? And I guess all these data are open to access, because this type of the images you will obtain will be very interesting for the other communities.
Yes, for sure. So we are, as I say, we're meeting tomorrow. We've got a special edition of the International Journal of Greenhouse Gas Control, and we have 23 papers we propose to put into that. That'll be published next year. The deadline for the papers going in is February, so it should be published in March, April. A lot of the data is already on our website, and the videos and et cetera are on the website. We want to get this out as soon as possible. It all will be public access, so we're going for full gold access for all the journals that we're working with. And on the website, you can find out the individual researchers who are working on each particular aspect of it, and so they'll be more than willing to answer questions. We've been, from the very outset, we've been very outward focused on trying to get this information out because we know how important it is. I spoke at the London Convention 2 weeks ago to present some of this work, and it was really keen how they really wanted to get the information as soon as possible. And the model, the tool we're developing for use by the regulators will be online through the International Energy Agency Greenhouse Gas Control Group. So it'll be a free open access tool that anyone could use. Scientists can use it just for playing around for their models, and also regulators will use it. This was only half the project as well. The other half of the project was around looking at natural geological features, these so-called seismic chimneys, which are common to basins. Can they act as conduits for CO2? Should you start storing CO2 in the bottom underneath them? So, as I say, it's a very large, ambitious project, and we've been very fortunate it's worked so well, but everything will be public access. So.
Any other question?
So you mentioned that you lost 2 days. How long was the campaign as a whole?
It was 31 days.
Okay.
So we went out of Aberdeen. We did it on 2 phases. We went out and did some work. We did the drilling or the pipe emplacement over the first couple of days because we had engineers from the cellular robotics company, and we had some geophysicists out there that had some specific things they wanted to do. After 5 days at work, we gave 2 days to do that insertion of the pipe. It happened in 20 minutes. It was amazing. Although it did cost £500,000 for that piece of kit. But then we came back in and went back out and said we lost just 2 days to bad weather, one of which would have been inshore anyway. So.
Okay. And you mentioned that there was a lot of challenges. It was very difficult in terms of engineering, and you showed us that you've achieved a lot. Is there anything you wanted to do that didn't work?
We were perhaps a little too conservative. We started on a very slow release rate of the CO2. We had 3 tons of CO2 down there. We actually only used 750 kilograms because we wanted to make sure we didn't create massive pock marks because we wanted to look at the changes in the sediments as well. It was quite important. Things we didn't do, we had an issue the first time one of these seismic chimneys, we wanted to drill it. We were using the BGS rock drill. We had to physically drill one of these offshore structures, which has never been done before. The first time we did that cruise, unfortunately, the research vessel we were using was having a contractor was doing some work on there, and they dropped a screw into the engine and destroyed the engine. So the cruise got cancelled. So the challenge was trying to get another cruise in a relatively short time. Unfortunately, the GMR team came through, and we relocated some funding within the project and some institutional funding to pay for that second cruise. So it wasn't without its interesting moments and lots of sleepless nights, but it did work phenomenally well. I've got some very incredible engineers who look about 10 years older now after the last year. So, yes.
Thank you.
Other question?
Obviously, thanks very much for the exciting work you perform. Obviously, it's a very shallow release of CO2. My question is about how comparable is the results with the deep release of CO2 from the storage reservoir. Obviously, GoldenEye is a very deep reservoir, so as CO2 flows through the leakage path, it would interact with the many minerals, release many things, and the pH behavior would be, I guess, different. Yeah. This is my first question. The second question is, did you have a chance to look at the isotope behavior of the environment as you release the CO2? Thank you.
Okay, I'll address those in part. There's been many projects looking at the deep reservoir and how you monitor deep reservoir release and fracturing of cap rocks, etc. As you say, GoldenEye is 2.5 kilometers deep. It has 2 cap rocks, which is what makes it a very good storage reservoir. Why Shell were proposing it. We didn't address that release at the deep, mainly because, as I say, a lot of money has already been spent, and there's a lot of good projects, particularly from BGS, and obviously Equinor are monitoring the Sleipner site continually, and so there's a lot of work being done on risks, projects called Risks and Dissects, where they're looking at what happens to mineralogy as you release CO2 at the very deep. So part of the work we're doing is we have got a pulse tube which can take core columns of rock, basically, and we can expose them to CO2 under pressure and temperature that are equivalent to what you'd get 2,500 meters down, and looking at the chemical changes there. So we're doing that on a sort of a relatively small scale project. So we were really focused on this, what happens when it gets to the environment. We do know on our basically stylized how we'd monitor the area. The areas you really want to monitor first and foremost are either existing geological features or anthropogenic features, such as the plugged and abandoned wells that we know are prevalent. So in the GoldenEye area on its own, there are 7 plugged and abandoned wells. We put one of our monitoring stations next to one of those as well. So part of that tool we're developing will be how you maximize your potential to detect leakage. And for the most part, the leakage in the models is actually going to be where you inject, or it's going to be through one of these existing features. On the isotopes, you saw the gas samples being collected from the bubbles. We have a project, Anita Flora is one of our postdocs. She's just about to join us as a full staff member in the new year. She's looking at the use of isotopes. And we also use a series of tracers in the gas stream, so not just inert tracers such as the CO2 isotope fractionation, which is very different to the natural background CO2, of course, but also we use SF6 and some perfluorocarbons, basically representing a balance of compounds that were reactive and non-reactive. So part of that around there was also driven by discussions with the operators, such as Equinor and Shell, was how you would label your stored CO2. If you look 20 years from now and we're using lots of North Sea reservoirs to store CO2, and there's a leak, but you have multiple operators, the operators would want to know which operator is causing that leak, because they would lose their tax credit. So we're also looking at how you would trace, in very quick time, development of CO2 monitoring systems that would look at isotopes. And we have a in-situ methane sensor in development at the moment that we will also monitor in situ the isotopic ratio in the methane as well. And we'll try and expand that in the near future into CO2. Hope that answered your question.
Okay, I think it's time for the last talk of this panel. Now, Ronny Pini from Imperial College London will introduce us laboratory studies to understand controls on flow and transport for CO2 storage. He's investigator of several EC-founded projects and also for the Science for Clean Energy project.
Thank you. Good morning, everyone. Also from my side. Yes, so we're going to have a small journey into the lab now. So I'm going to show you some of the work we've been doing in the last few years, trying to understand some of the properties of rocks in terms of the flow properties and the transport properties in the context of geological carbon storage. Just briefly, to put things in context, we heard also from the previous presentation, so we are dealing with a technology where we are injecting CO2 into a deep porous formation. We are looking at things that are found at least at 1 kilometer depth, and the technology is quite interesting because you can actually access a different type of geologic formation. So we can look into depleted oil and gas fields. These are quite interesting because we tend to know a lot about these rocks because of the oil and gas exploration. Deep saline aquifers, these are actually quite widespread and have a lot of potential storage capacity. You can couple the injection of CO2 with the recovery of oil to push even more oil out of the ground, and this actually gives you an economic incentive. And then there are also other type of rocks which also present very interesting characteristics for the CO2 storage, and we heard before about the Icelandic case using basalts. And indeed, reiterating some of the few concepts that we heard before, so where are we at the moment? Actually, the technology is not new per se, so the oil industry have been injecting CO2 for oil recovery since 30, 40 years, and for instance, in this unit alone in Texas, they injected up to almost 100 megaton of CO2. Luckily enough, so there have been other, so the difference there actually, they were not looking for storing the CO2, so they didn't look into trying to quantify how much CO2 would stay into the formation. But other projects have started since then, specifically to understand the CO2 storage capacity of rocks, and there have been a number of megaton scale demonstration projects. The most famous one was mentioned already a few times, is the Sleipner project in the North Sea, and up to date, they've injected up to 17, 20 megaton. So I would say that at the moment, this is where we are. So the technology is demonstrated at the level of 1 to 4 megaton per year. This is the size of those projects, but it was mentioned before, we need to go to a much bigger scale if we want to have an impact on reducing emission, and that scale requires therefore injecting CO2 at the level of gigatons, so 1,000 times more. And that's quite important because, again, reinforcing some of the statements were said before, as of now, geologic carbon storage is actually the only approach that we have to isolate very large volume of CO2 from the atmosphere. So in the research that we've been doing in my lab, we have been focusing mostly on these deep saline rock formations. This is because indeed they're quite widespread and they're found everywhere around the planet, and they're supposed to have the largest storage capacity. And so when you inject CO2 into these formations, CO2, even though it's at high pressure, is still buoyant, so it's still less dense than water, so it will tend to raise up to the surface again. So what you need is a sealing formation above your storage formation to keep the CO2 there. And if you focus now into the formation itself, and we start looking into what are the mechanisms that are there to actually prevent the CO2 to come back from the atmosphere, this is actually what is happening. So as you inject the CO2, this is really a two-phase flow problem, right? So CO2 will start displacing some of the water, but also rising up to the caprock because it's less dense than water, and because of the gravity force, it will start flowing along the caprock. And therefore, so the structural trapping is quite important to initially keep the CO2 there and let other mechanisms start playing a role. And a very important one is what we call capillary trapping, and this is basically when the CO2 flows through the pores of the rock, it leaves behind blobs of CO2 that are basically isolated and trapped by capillary forces into the rock. Once they are trapped, eventually the CO2, because there is some affinity with the water, will start dissolving into the water. And actually, we are going to talk a little bit about that later on. And if you wait long enough, eventually the CO2 will react and mineralize. So there is a time element here. So when you move from left to right, time goes by. And accordingly, there is also an element of increasing storage security. As you move from CO2 that is still present in the gas form and therefore still mobile to CO2 that is actually now dissolved into the water, actually moving downwards, which is quite good, and finally immobilized as a solid phase. So the challenge is now for us working in the lab is to essentially try to understand these processes and how they basically interact with the rocks, right? We know that the subsurface was not designed by engineers, so it's quite complex. It's a natural environment, so you have heterogeneities in space and time in the properties of the rock, but also the chemical properties of the rock. And so what we want to understand is how basically this heterogeneity will actually impact the trapping and process. So as an engineer, what we want to achieve eventually is an industrial operation where you try to exploit, at best, the pore space in the subsurface, and therefore improve also our estimates, the reliability of our estimates in terms of the storage capacity. And so what we are after is therefore to understand these processes at various scales, and particularly we work with laboratory rock cores, and understand how the heterogeneity, particularly the one that you cannot resolve, is actually affecting these processes. So at Imperial, we have built in the last few years instruments to basically expose rocks to the conditions that you would obtain in the subsurface. And so that's an image of our core flooding systems. In essence, here you you are able to expose rock cores of 10, 20 centimeter long to conditions that you have in the subsurface, so high pressures up to 20 megapascal and high temperatures, and you can inject indeed high pressure fluids. So you can inject supercritical CO2 and brine and let them circulate through the rock. And a unique aspect here is that while this is happening, we are able to image what is actually happening inside the rock. So we are able to image the flow of the fluids in the rock, and because the system is basically embedded in this case in a medical grade CT scanner, so the rock core will sit there while it's exposed to CO2 and water, and we can take scans over time as the fluids interact with the rock. And this is an image here showing a little bit, if you want, the workflow, right? So you have your rock core here. If you take a dry scan of your rock sample, you will get an idea about the heterogeneity in the properties of your rock. In this case, is the heterogeneity in the pore space, so the available volume to the gas. Once you start injecting CO2 and water, you can map where the CO2 and the water are lying in the rock, and you see that it is quite heterogeneous. And we are also now using another technique called positron emission tomography. So this is an X-ray computed tomography scanner. Using positron emission tomography, we're able to actually track the movement of very small quantities of tracers dissolved in the water to understand how they move through the rock in time. So looking at some of the data, so what we are after are important properties that describe the multi-phase, the two-phase flow of CO2 and water in the rock, and one of these important properties is the capillary pressure curve. This is shown here. These are various measurements on different type of rocks that we've done in the lab, and this is quite an important property because it relates the capillary pressure, which is a parameter that depends on the depth and that you can control through the operation, to the actual saturation. So you basically you know, depending on where you are in the curve, how much CO2 can be present in the pore space. And essentially that's basically the region that often is encountered at depth, and what we see is that basically 28 to 80% of the available pore space can actually be filled with CO2. Very important though is also how to mobilize the CO2. So as I said before, once you inject the CO2, it will be trapped in the form of blobs. It is just a simplified schematics and immobilized in the pore space of the rock. And these data are typically presented in this sort of plot where you have now the residual amount of CO2 that you can trap as a function of the initial saturation, so the level that you achieved on your curve. So if you would trap everything, you would stay on this solid line here. We are slightly below that, so some of it will be mobilized again. But as you can see, we are trapping 10 to 40% of the wet pore volume, or in other words, about 50% of what was injected. Another important feature here to show is that the characteristic shape of these curves with this basically inflection point here tells you that in this region you're quite sensitive to the capillary pressure. So you have strong variations in saturation if you vary that properties just a little bit. And actually we see that this is indeed what is causing this heterogeneous distribution of CO2 in your rock. These are now scans again of different type of rocks with the pore space shown here, and at the bottom the corresponding distribution of the gas, of the CO2 and the water in the rock. And indeed, because of the very low viscosity contrast, the movement of CO2 is really strongly affected by the small scale heterogeneities of the rock. And this is actually what leads to this very heterogeneous distribution of the CO2. And our work has been so our effort here has been to try to capture this quantitatively using models and to understand, to really understand why this is happening. So we essentially are doing also some numerical modeling work where essentially we now use the images that we obtain from the scan to basically, if you want, divide your rock core in different elements with different properties of the rock. And one of those properties that we are actually interested in is the capillary pressure curve. So essentially in every of these different elements you can use a different properties, and you let your model predict how the distribution of the CO2 will be. And here you have the gas saturation as a function of distance in one of these rock cores, and you see the symbols are what we measure experimentally, and you see that the model by actually having this variation in the properties of the rock, is able to capture quite nicely the process. I'm not doing time. Now the question is, how is this very important? Are these very small scale heterogeneities important at a large scale? And this is what I'm trying to show in this slide here. So you can easily extend this characterization to 3 dimensions. So you can have a 3D map of your rock core with these different properties distributed. And these are actually simulations that are being performed by colleagues at Stanford, where you now populate with these very small scale heterogeneities a larger let's say volume, or in this case area. You see a 5 meter by half a meter size with these very small heterogeneities distributed in space. And they run 2 different simulations where you let CO2 rise due to buoyancy forces in this system. One is where you account for those heterogeneities, and one where you basically neglect for heterogeneities. So here now the coloring is not ideal, but essentially what is showing here that when you have these heterogeneities, the CO2 plume raises only up to half of the full domain, and it's actually immobilized in the system, while in the homogeneous system, where you neglect about heterogeneities, the CO2 actually reached already this level here, and some of it has already escaped the system. So these very small scale heterogeneities are indeed quite important, and accounting for them is important to predict how the CO2 will distribute in the subsurface. Very briefly on the dissolution by trapping, as this is something that is quite important as well. So the CO2 will dissolve into the brine, and actually our interest is now to know how this brine enriched with CO2 will distribute in the rock over time. And there are 2 different mechanisms that can help with that. Obviously, you have some advective flow in the subsurface, but there is also a very interesting phenomenon, which is the one driven by buoyancy, because the density of CO2-rich brine is actually larger than the density of fresh brine, and therefore you will create an instability in your system. So we are doing experiments to study both. I mentioned before we can use different rocks. I will go a little bit quick here now, but essentially we do experiments where we inject a small amount of a tracer, and we observe the movement of the tracer through the rock, and we can relate this observation to the different textural properties of the rock. And we see that depending on the type of rocks that you have, you can have very different patterns of heterogeneities. And the interesting observation is that the more heterogeneous is the rock, actually, the better the mixing will be, which is actually quite good. And moving quickly to the other phenomenon, this is a simulation showing essentially when you have CO2-rich brine on top of fresh brine, you create this instability, and the CO2-rich brine will start flowing downwards in this, forming these very interesting convective patterns. And if you quantify this process, you're interested to know, what is the contribution to mixing. Here I'm plotting the degree of dilution, so the amount of the volume that you're occupying with the CO2-rich solution as a function of time, and diffusion is given by this line here. You see that as soon as this convective process starts, you actually start moving much faster, so your mixing is becoming greater, which is obviously very good news, because it means you are more effectively distributing the CO2 in your system. And we have also developed experimental protocols to now image this in the laboratory in 3 dimensions, and this is now giving us indeed the tool not only to observe directly this process happening through experiments, but also observe actually the characteristic patterns that are formed as CO2 interacts and dissolved in the water, that allow us to really better parameterize the process. Let me go to the conclusion very briefly. Geological sequestration is actually a quite interesting problem scientifically, because you have multiple physical processes happening at the same time. This gives us a lot of scope for research, obviously. And what we are deploying here are experiments where we try, which are augmented by using imaging technology that allow us to observe these processes in situ. A few messages is that we see that actually small-scale heterogeneities are quite important in controlling the transport of CO2 and the trapping of CO2 in the rock, and we need therefore models that are able to account for these heterogeneities to make reliable estimates of the amount of CO2 that you can store. And understanding indeed the interplay between the flow and heterogeneities is indeed very, very important for us as engineers to really engineer strategies to optimize the use of the available pore space. And with this, I would like to thank you for your attention, acknowledge the sponsors, including this project here, Science for Clean Energy, which allow me to do some of this research. Thanks a lot.
Is there any question?
Hi, in some of the EUR processes that you talk about in North America, people sometimes use a process called sort of WAG, the water alternating gas. And I'm just wondering from your research whether you think that might also be a process that could work quite well in carbon capture and storage, where you sort of alternate, have a pulse of water every now and again rather than always injecting just CO2.
Yeah, it's a very good idea. And indeed, there have been a few studies who are looking into that. And indeed, one of the advantages of doing this alternation between water and CO2 is that you can enhance this, what we call this capillary trapping. So because you re-inject the water, you basically immobilize much more quickly the CO2. The question is now how this feed back into the injection pressure, right? Because by having now CO2 immobilized in the pore space, you are increasing the pressure drop because there is less space available for the flow. But it's an interesting approach, and indeed, I think there is a lot to learn from those techniques, and people are looking into ways of exploiting this.
Thanks, Ronny. Very interesting talk. So, in your research, you said, have you noticed are there some like grain size or pore size or some compositions of rock can make the capillary capability change or anything interesting?
So you're referring to the capillary trapping properties, yeah. So in this plot that I was showing here. So this is actually all this data are combining sandstone and carbonates. Essentially, we looked at these are being the two major, potential storage reservoirs for saline aquifers, and we actually don't see very strong variations between the two type of rocks.
So how about some like tight rocks, maybe?
Very tight rocks. Yeah, so we didn't do these experiments on rocks that are not considered reservoir rocks. Like these are fairly porous, high permeability rocks.
Okay, thank you.
Other question?
Alberto.
Take the microphone because we are being recorded for posterity. So at the beginning, you said that the rocks have not been engineered, right?
Yeah.
But you actually show that this heterogeneity seems to be helpful in both storing and increasing the dispersion of the CO2 in the subsurface. So have they not been engineered for those purposes? What's your take on there?
Well, that's a philosophical question, I guess. But no, I mean, what I meant here was simply to say that obviously we don't have, we can, in chemical processes, you have a chance to change your porous materials to make it, more efficient, for instance. Here, we cannot really change the rock, but we can basically change the operation to exploit essentially what the environment is, right? So, and indeed, by learning that heterogeneity, for instance, can help you in spreading more CO2, creating more interfacial area, and dissolving CO2, we can come up with solutions. So that's basically my take.
Thanks.
If there is no more question for Ronny, I kindly ask all the speakers of this panel to come here for the public discussion.
Thank you.
You have any question for the panel speakers you haven't asked before?
Hi, I just wonder from all of your different investigations and work, whether you've formed an informal idea maybe of the sort of carbon trading price, the ETS price, that would start to turn the work that you're doing from remaining in a scientific manner to really being able to roll out at scale.
Yeah, so in terms of our operations, the price of carbon is more or less the same as the operations at our site. But then again, this price is very dependent on the stream that we are capturing, and in terms of many industries where you have more dilute streams, you would see this price go up quite significantly. So we are at the maximum low now, and I guess it would have to probably double, in some cases be even higher.
Yeah, we having sort of spoke to Shell and then being involved in sort of development of and rollout of the Northern Lights project, you're still looking at between $60 and $90 a ton for it to become cost effective. And again, as Sandra said, it's often around those disparate sources. So the Northern Lights obviously is going to have a hub where it'll collect from steel and cement works, try and collect, get all the CO2 together and take it off a ship. The Peterhead project, which originally was Shell and Scottish and Southern Energy, was to build a new power plant with the capture of CO2, state-of-the-art, right there, 25-kilometre pipeline out to the Fergus pipeline, which would then take the CO2 right out to the Goldeneye platform. That becomes more cost-effective, but again, you still need some balancing tax aspect so that the companies involved can get their money back. And that's, I think, what is stopping any full-scale demonstration other than the Equinor project. It's like no.
I mean, the capturing part is by far the most costly part of it, and then it's very much dependent on the CO2 concentration. So, in case of, for example, aluminium smelters, I mean, the CO2 concentration in the stream is maybe around 2%. So the prices go, up as the concentrations goes down. And then, of course, if we are going to deploy direct air capture of any sorts, the costs go even higher. There you are dealing with 400 ppm, so yeah.
Could I just ask a quick follow-up question, which is about, because you talked a little bit about offshore monitoring and public perception, in terms of offshore and versus onshore capture and storage. What's the panel's feeling about public acceptance of onshore storage at different scales?
Should I go that one first? So we went originally for offshore for the simple reason after the public opposition to the Katzin project in Germany, we knew that it wasn't going to be onshore, probably wasn't going to develop on mainland Europe in any time quickly, and also the capacity particularly for the UK is nearly all offshore.
In terms of conventional CCS onshore, I mean, this is a very, very difficult in terms of the public acceptance. For us, this has not been a problem, but of course we are doing this differently, and I guess also the Icelandic public is used to a lot of geological activities, both natural and anthropogenic. So I think the public is probably a bit different in Iceland in general, but the surveys that have been made in Iceland show that the public there is at least very much for this kind of operations, and it does really help that it is a safer way of storing in terms of leakage. So for onshore operations, maybe this could be more accepted concept, onshore.
Yeah, I agree. So I think the Icelandic case is a very good example on when you communicate and you're very open with what you're doing. Actually, you get people on board and you can work easily and safely onshore. Within Europe, people are thinking now about storage hub, like using the North Sea as a large reservoir where various countries could basically contribute to, and I think also they're having a commitment from various companies to characterize a big large hub and having a concerted action there. I think this would also be very helpful to see that actually we work together to basically make this process safe. And going back to your question on the costs, I think probably I agree with those numbers. Probably one of the things that have been missing is a business case for CCS, and I think some of these ideas of, for instance, coupling CCS with hydrogen production is maybe making this sort of business case, right? So if you think about a society that moves towards using hydrogen as an energy carrier, but the way we produce hydrogen at the moment produces a lot of CO2, so there suddenly you have a business case for actually doing something with the CO2 and, for instance, storing it. And hopefully this is a way to make it happen on a large scale.
I would have a follow-up one from the offshore versus onshore. You've discussed public acceptance, but in the more general view and for the future, what would drive one being chosen rather than the other? There is obviously the scientific challenge, there is the monitoring challenge, the cost and so on. Where do you see that going, and the share of onshore versus offshore, and what would determine the ratio between the two approaches?
Who can better answer this question among you? Who wants to start?
I can sort of start. So basically, a big part of the project for we were doing was actually to get to a cost. What would it actually cost to monitor a large area of the seabed in terms of trying to pick up a leakage? So it's the confidence and the cost. And it is expensive. It will be expensive. Although, if you look at the environmental impact assessment that Shell did for the GoldenEye, for the Peterhead project, they were talking at monitoring for 50 years, which the legislation says. And the initial stages of monitoring were on the order of 200,000-300,000 a year, just for the sort of seismic, to get the 4D seismics over time. And they were going to do a whole chemical and hydrographic monitoring and everything, so we took a lot of that out and just said we need to focus on the areas where there is a higher risk. But it is still going to be expensive, and it's a case of building confidence around the tools we've got. Can we believe what the data is that we're getting from our sensors? The public will always think that, we get constantly trolled by people, particularly in the States, who are really anti-CCS, and they hate the STEM project because Shell are a partner. So they're basically saying, surprise, surprise, they're showing that the results are quite promising, but of course Shell are a partner, so what do you expect? We'll always have that, and that perception issue is just a case of we are driven by facts, just present the facts. We should be very careful about giving an opinion beyond what is driven by the facts. And I know your project has a lot of public outreach and things like that, and it's very key in the QUIX project, which was another marine demonstration project about 8 years ago. Spent a lot of time working with the public, and we're doing a new rollout of public perception testing at the moment in the Aberdeen area, in the northeast, to actually look at how the public perceive offshore CCS. Scotland, the Scottish public are much more supportive than the broader British public, because obviously they see it as a big industry, and the companies involved have put it forward in the same way that Iceland is. It's a big industry. It's a big component of the potential economic return for Scotland.
I think in terms of onshore, offshore operations, we would probably always aim for offshore for the large scale, like the large scale operations. I don't think that we will be injecting gigatons onshore anywhere, but to achieve these numbers that are proposed, if you're going to be able to store all of the CO2, we will probably need a lot of small scale operations that probably will also be onshore, especially the ones that are where you have point source of CO2 located near a suitable geological formation. So I think in terms of these, you would want to do the onshore one where you have all the ingredients you need for a successful CCS, because you get the cost down. But for the large scale, definitely offshore.
This is a question for Dr. Sandra. Correct me if I'm wrong. You said that the carbon dioxide that you inject into the basalt, they solidified within like 2 years instead of 1,000. What's the reason for the rapid formation of?
So there are two reasons behind this fast reaction. So firstly, we are injecting into very reactive rocks. So we have a lot of these cations present to combine with the injected CO2. But then we are also dissolving the CO2 in water. So this is also part of, accelerating the process.
Thank you.
I was a little bit curious. Sandra, earlier you mentioned that the science is known. It's just a matter of bringing it to practice. The technology for monitoring the leaks, we are working on it. Something is coming up. So Ronny, what is left for the academia? Are there big questions that we need to address? Like, for example, this reactivity, Sally was expecting 1,000 years, and now everything happens in a couple of years. What's in there for us?
Well, yeah, so that's a specific case, right, of the reactivity. Obviously, in the lab, what you can do, you can accelerate processes. So I think when you think about the other rocks where reactivity is much slower, you can actually study this in the lab and make prediction of what would happen, eventually in hundreds of years or so, because you can inject many pore volumes of fluids in a shorter amount of time. At the same time, I think we are also, this issue about understanding better what's happening below the scale that we can resolve features in the subsurface is quite important, right? Because obviously there is progress also in seismic monitoring, so they're getting higher and higher resolutions, but still, there is a limit to what you can actually see. So I think what we're trying to do here is to develop workflows where you can basically create this link between the process that at the end of the day takes place at the pore scale, because that's where everything starts, right? Where the molecules of CO2 start interacting with the molecules of water, up to a larger scale where then you can start making connection with what you can see, during the operation. And there is still work to be done.
Yeah, also, just to comment on this, what I actually mean with this is that we just have to start operating. We just have to go to the field and start to do more of these injections, because this will always be different from what we're doing in the lab. We build on what we learn in the lab, but then for each CCS activity, we will always have to do a very site-specific characterization with all the science involved there. And then, this will always come with some complications when you move from the small scale and to a larger scale. So this is where we need to fill in our knowledge gaps. This is the pressing issue in my mind, that we are just not injecting.
Yeah, and I think, if I can add, I completely agree with that, right? So I think if you think about, again, the chemical industries, right? So we, in the 60s or 70s, a chemical process, we were emitting everything into the atmosphere, right? So, and eventually, regulation started and saying, now we need to, capture a lot of these pollutants. And so things can be improved over time, right? We just need to start doing it. Then eventually we'll get to a point where, we get a better understanding of things and we can make processes even more efficient, but we just need to start doing it.
Yeah. I mean, that's what you always hear, is basically we just got to start doing it. I mean, the classic one from my friend Owen Tucker at Shell is, at the moment, we're releasing 100% of the CO2 we produce. So even if we start storing... Yeah, we've got complete leakage at the moment. So anything we can do towards showing, even if it's only held for 1,000 years as opposed to the models of 10,000 years, it's a start.
If I may, another question, and then I promise I will leave the microphone to somebody else. Let's suppose company X does the carbon sequestration somewhere, and I think I understand that the regulations at the moment are that the site needs to be monitored for 50 years, correct? Let's suppose 30 years down the line, your instruments are beginning to detect a leak. What can we do at that point?
So at the moment in the marine system, not a lot. Basically the remediation aspect is sort of non-existent. The control mechanism at the moment says that if you get leakage, and at the moment for Equinor, the way that is actually monitored is by injection pressure. So if they suddenly lost the injection pressure, they assume they've got a leak somewhere, so they just stop. The 50 years comes in, that's the maximum time they have to monitor. If they can demonstrate containment within, for every year, at some point the national body takes over. So in the case of the UK becomes part of the Crown estate, that stored reservoir. And no one's really said what could happen. In the marine system, effectively, they've looked at ways of coating the seabed with cement. And effectively, they're just relying on the fact that any leak at the seabed would probably be at a slow rate, unless it was a blowout, and a slow rate would have a relatively minimal impact on the marine system. But of course, you're still then losing containment, so that CO2 is still going back into the environment in some way. So, and a large blowout is potentially, well, I think most of the models show blowouts aren't the real threat. It's a slow leakage that you don't pick up very easily. But there's no real remediation process in place apart from stopping injection. But as you say, if it's 30 years after you've stopped injection, there's a challenge. I don't know what the land... There is none, is there?
Thank you for a really interesting session. In this room, we sometimes have lectures and sessions like this with the nuclear industry, and they're dealing with their nuclear waste. And the language used there is geological disposal facility. We're talking here about carbon capture and storage. So I wonder what our thoughts might be on that, in particular for Iceland, where you're not really storing the CO2. You're getting rid of it completely. So arguably, you're doing a disposal facility in Iceland, whereas what we might have in the North Sea is a storage facility. What do you think the public view on this difference of vocabulary might be, and how it would affect their acceptance of whatever process is gone ahead as an industrial scale?
I never got this one before. But yeah, in Icelandic, we actually refer to it as disposal. So I haven't thought it through, but it's an interesting point. And of course, this is actually one of the things that we have been asked. But what if we need the CO2 later on? Exactly. So interesting point.
The sort of nomenclature around storage rather than disposal came specifically out of the marine system, because under UNCLOS, the law of the sea, and also OSPAR, disposal is something entirely different to storage. Disposal, you are not allowed to dispose of pollutants into marine systems. So that's sort of where they took the approach of it's storage rather than disposal. And I think that sort of bled back onto the land, and now it's counted as storage. But yes, and we actually offshore, you're probably more likely to be able to get it back at some point than you are if you've turned it into a mineral. So.
Would the public be more accepting if it's disposal, or more accepting if it's storage?
Yeah.
I'd say probably storage is more acceptable than disposal. Because disposal just has that natural, it's a waste and it's nasty, and
I just don't want to go through with the name change after, you know,
years.
after all the years of efforts, but yeah. Yeah. We'll have to think about this one.
Yeah.
Sleep on it.
Our social scientist side of our project are always saying, call it carbon dioxide capture and storage, not carbon capture and storage,
Yeah,
because
that's
plants are carbon capture and storage. And so they're constantly hitting me and berating me for just saying carbon capture and storage, and I should say carbon dioxide, because then it implies carbon dioxide the public know is bad,
Yeah.
and therefore carbon dioxide capture and storage can be viewed as something more positive.
Okay, I think the panel is over. Now it's time for coffee break. Thank you to all the speakers for this panel. It was very interesting. Thank you very much.